Okay, good day. This is AP Calculus. I am Mr. McCulley, and this is the presentation for section 3.1, concavity and the second derivative test. Let's get right into it. So today we're going to determine the intervals on which a function is either concave up or concave down. I don't know why I have a question mark there, but hey, what are you going to do? Apply the second derivative test to find relative extrema of a function. So here we go. Let's talk about this. Concavity in the second derivative test. Let f be a function that is continuous and the second derivative exists on a to b. So if f of x, or f double prime, and that's what I'm calling this right here, double prime, f double prime of x is greater than 0 for all of the values of x on the AB, then f is concave up on a to b. If the second derivative, or f double prime of x, is less than 0 for all values of x in ab, then f is concave downward on a to b. And then there are formal definitions for you to look at before you start the practice work on page 191. All right, so let's talk about concavity as far as a picture. So the second derivative test determines how a function is curving at any given point. So the first derivative determines the slope of a tangent line. The second derivative determines how it's curving. If the second derivative is positive, then the function is concave up. So for instance, a graph that does this is curving up. This is a concave up function. If the second derivative is negative, then the function is concave down. So a concave down function will look like this. And that is what concave down will look like. All right, let's move on. Points of inflection for the twice differentiable function. This is a term that is quite often used on the AP Calculus test. A twice differentiable function means that it can be derived at least 2 times. That doesn't mean that it couldn't be derived more, but it has to be able to be derived twice and still have something that's other than 0. All right, so just going back to it. So for the twice differentiable function f and a point x equals c in the domain of f, if f double prime of c is equal to 0 or f double prime of c does not exist, then f or c, f of c may be a point of inflection, and we're going to have to test that. And it is a point of inflection when the function changes concavity at the point. So this is kind of like the critical numbers that we talked about in the last section. They're not called critical numbers, but they function basically the same way. So points of inflection basically occur at the critical numbers of the second derivative. Now that doesn't have to be a point of inflection. It can be a point of inflection, so you have to test it. And one way that we can test this is again using a sign chart. But again, that is not necessarily enough evidence to prove the concavity of the function. So let's tie some of this stuff together. Well, before I do that, I suppose let's talk about this. The second derivative test. The second derivative method is an additional method for finding extrema. We've already found one. We already had one with the first derivative test, but we have another possible way, or another possible method for finding extrema. So if f is a function such that f prime of c is equal to 0, and the second derivative exists on the open interval containing x equals c, if f double prime of x is greater than 0, then f has a relative minimum at c comma f of c. So basically what's that saying as far as the graph goes is, let's say you find this point right here, this is my c, and you find that f prime of c is equal to 0. All right, well, if you find that over this interval right here that f double prime of x on that interval is greater than 0, you can say, okay, that's an extrema, and because it's concave up, this has to be a relative minimum. Now, the opposite, that should be an n, not an m, but we need to keep moving, so you can fix it on your own. Anyway, so if I have a function that looks like this, that's not very good because I don't want it on the y-axis. If I have a function that looks like this, and this point right here gives me f prime of c equaling to 0, which is what I get at a relative maximum, or at a critical number, f prime is equal to 0, and this is my c. I don't know why I was writing this. And I talk about this particular interval right here. If over this interval, f double prime of x for any x in that interval is, excuse me, it will be less than 0 this time. If it's less than 0, that makes it concave down. So this thing here is going to be a relative maximum. All right. So let's tie some of this together. So here's what I'm going to do. I'm going to give you a situation here, and then I want you to pause the video and kind of draw an example that has these two things of the situation. Just take a quick pause, draw it, and then come back and see if what you've drawn is the same as what I have here. So the first derivative, so here's my first situation. If the first derivative is positive, and then the second derivative is positive over some interval, and just to let's see if we can turn off. I don't want to do that. I want to turn off these numbers because I don't care about the numbers. So just over some interval, we'll call it A here, we'll call it B here. Over some interval, draw a section, or draw a section of a curve where the first derivative of that thing would be positive and the second derivative would also be positive. So pause and draw. All right, we're back. I hope you've got a good drawing. Since the first derivative is positive, it should be increasing over this interval. And since the second derivative is positive, it should also be concave up. So a possible graph might look something like this, with endpoints here. And I guess I kind of screwed that up there because I kind of give you a point of inflection. It should always be concave up right there. So there's our first situation. Second situation, draw where the first derivative is positive and that the second derivative is negative. So pause. Okay, I hope you have a good drawing there. So once again, let's change so that we don't have any numbers. And we can call this A again and this B here again. And so let's see here. We need the first derivative to be positive, so it has to be increasing over that interval. And since the second derivative is negative, it has to be concave down. So we want to have something that looks like that. All right. Next possibility, situation 3. So this time I want you to draw a curve such that the first derivative is negative and the second derivative is positive. So pause. And while you're pausing, I will get rid of that. We'll go back again. We're going to go A and B. And so since the first derivative is negative and the second derivative is positive, it should be decreasing over this interval. And because the second derivative is positive, it should be concave up. So if I go from here to here, I'm definitely going to be decreasing. And I want to draw in a curve that's concave up, so I'll have something that looks like that. All right, last one. Hopefully you're getting the hang of this. So this one I want you to draw over your A to B. I want you to draw a function. And again, there's my A and there's my B. It's not a very good B, but we'll get there. All right, so the first derivative has to be negative and the second derivative has to also be negative. So pause and draw. And we're back. So since the first derivative is negative, it has to decrease over that interval. And since the second derivative is negative, it has to be concave down. So we're going to get something that looks like that. All right, so let's get to some examples. We'll start for a first one. And the first one comes from page 195, number 24. It says, find the points of inflection and discuss the concavity of the graph. All right, so points of inflection, again, is going to be where the second derivative is equal to 0. So I'm going to go f prime of x. We're going to take the first derivative of this. And this, since this is a simple polynomial, we can just do the derivative using the simple power rule. And I'm going to do 4 times 2 is 8, and that'll give me x to the third. And then I'll have minus just 8 because of the derivative of x is just going to be 1. And the derivative of a constant is 0. And so the second derivative, f double prime of x, is going to be, let's see here, 3 times 8 is 24, and that's going to be x squared. All right. So let's talk about this particular graph. We have a possible, let's see here, let's do it all. Let's say a possible point of inflection over a possible point of inflection at x equal to 0, because that's the only value for x that's going to cause the second derivative to be equal to 0. So let's talk about the concavity of this thing. And I picked this one especially because I'm going to plug in my 0 there. Now, if I plug in a negative number, let's say we'll choose negative 3. Negative 3 squared is 9. 9 times 24 is going to be a positive number. So I'm going to have a positive, so that's going to be concave up from negative infinity to 0. And then if I plug in 3, I'm going to get the same number. I'm going to get a positive. So for this one, there are no points of inflection. And this function is always concave up. All right, no points of inflection because I don't have a change of concavity. And since this is the only place where it could change concavity, and it's concave up on the left and concave up on the right, it's certainly got to be a function that is always concave up. And if you go ahead and graph that, you will certainly get something that I'm not 100% sure. I do know it goes through 3. And I'm not even sure if it'll go through the x-axis, if there's anything that'll go through it, but it probably looks something like that if I were a betting man. But you can check it. I might be wrong. Probably shouldn't have graphed that since I'm putting it on YouTube, but what are you going to do? Okay. Next one, it says find the points of inflection and discuss the concavity. So here we're going to do a trig function, and here we're only going to be talking about values of x from 0 to 2 pi, so just on the unit circle. So my first derivative of this function, let's get the proper tool. F prime of x is going to be cosine of x, and then the derivative of cosine is going to be negative sine of x. And so let's see here. The second derivative, f prime, double prime of x. The derivative of cosine is negative sine x. And then this will be negative cosine of x because the derivative of sine is cosine, so it wouldn't change the sign. And we need to know where that's equal to 0. Okay, well, how can I solve this? Well, we're going to have to kind of fudge this one a little bit. So what I'm going to do is I'm going to move this cosine to the opposite side. I'm going to say sine x is equal to cosine of x. So what values of x will the sine and the cosine be opposites of each other? One will be positive, one will be negative. Well, on my unit circle, there's only 4 places where the magnitude of the sine and the cosine, the x and the y, are equal. And that's at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. But there's only 2 places where they are opposite of each other, and that is going to be at 5 pi over, or no, this is just 3 pi over 4, sorry, and 7 pi over 4. That's where they're going to be opposites of each other. So my possible points of inflection are at x equals 3 pi over 4 and 7 pi over 4. So I'm going to draw myself a little sine chart, and I'm going to put in my endpoints. I'm going to put 0, I'm going to put 2 pi here, and I'm going to put my 3 pi over 4 here, and my 7 pi over 4 here. And so we have to discuss our concavity over this interval. All right, so if I plug in to the second derivative here, if I plug in f prime of x, I need something on this interval. Well, here I'm just going to choose this point here, this pi over, or excuse me, I'm going to choose pi over 2, because that point. And so the negative sine of pi over 2 plus the or minus the cosine, sorry, got to use the right one, sine of pi over 2 minus the cosine of pi over 2. Well, sine of pi over 2 is 1, I make it negative, minus 0, this thing is negative. So it's negative there. So I want to choose a point between here. Let's choose this point right here. We'll call it pi. And so f prime, and I guess I probably should, for this one right here, we should have pi over 2. We want to do, what did I say, pi? Yeah, I did. So f prime of pi. And I need to make these double primes. Sorry, because I'm plugging it into this equation right here to determine values. So double primes, we'll go back here, we get negative sine of pi, and then we have minus the cosine of pi. And so the sine of pi is 0. The cosine of pi is -1, so I get minus -1. That's going to be a positive. So I get a positive here. And then I need a value between 7 pi over 4 and 2 pi. I don't have a whole lot of room, so the only one that's going to come out nice is going to be, let's see here, it'll be 11 pi over 6. So let me bring this down a little bit. Again, second derivative, and we're determining the concavity over that interval. And so this is going to be f double prime of 11 pi over 6. So I'm going to have the negative sine of 11 pi over 6 minus the cosine of 11 pi over 6. And so the sine of this, I got negative, and it'll be, let's see here, since it's here, it'll be, the sine is the y, so it'll be -1/2, and then this one will be the cosine of, let's see here, it's going to be cosine, so the x value would be positive, square root of 3 over 2, and so this becomes a positive. Now, square root of 3 over 2 is bigger than 1/2, so this thing is going to yield me a negative value. I don't know what it is exactly, but it's a negative value. So I have points of inflection. I do have points of inflection here at 3 pi over 4 and 7 pi over 4. Those are going to be points of inflection. Why? Because it changes concavity at that place. So points of inflection. I've got, let's see here, it'll be 3 pi over 4 and 7 pi over 4. But I got to figure out what the y values are. Now, since we're doing, now points of inflection are actually on the curve, what we want to do is we want to plug into the original to get the y values for those. So the sine, let's see if we can get away, the sine of 3 pi over 4 is going to be square root of 2 over 2, and the cosine of, 3 3 pi over 4. The sine of 3 pi over 4, yeah, it's going to be square root of 2 over 2. Excuse me, the cosine will be negative square root of 2 over 2. So when I add those together, it's 0. Oh, that was nice. Shoot, that was good. All right, and then when I do 7 pi over 4, the sine value is negative square root of 2 over 2, and the cosine value is positive square root of 2 over 2. And again, we're right here, so the sine value would be negative and the cosine would be positive. Since they're the same magnitude, add them together to 0. That's awesome. Okay, so we have concave up, the intervals on which it's concave up. The intervals that's concave up is where it's going to be positive, so it's just going to be, there's only one open interval, and that's 3 pi over 4 to 7 pi over 4, and then it's concave down on 0 to 3 pi over 4, and that's going to be unioned with 7 pi over 4 to 2 pi, all the way to the end. And those are the two things that they asked for, so we are done. Okay, last one. It says, sketch a function with the following characteristics. So f of 0 and f of 2 is equal to 0. So these are zeros of the function. F prime of x is greater than 0 from, let's see here, is greater than 0 for values of x that are less than 1. Okay, that's all right. So that's it. So from negative infinity to 1, this thing is increasing because the first derivative is positive, so it's got to be increasing. At f prime of 1, we get, f prime of 1, we get 0. So at 1, we have to have a horizontal, not a horizontal tangent line. And obviously that's going to make us have probably either a maximum or minimum. And you might be able to figure it out already based on what we're talking about. And then for values of x that are greater than 1, the first derivative is going to be negative, so it's going to be decreasing. So it changes from increasing to decreasing. And then this thing says that f double prime of x is less than 0 or negative, and since there's no restriction, we're going to assume it's there for forever. So if I get a Cartesian graph here real quick, and let's turn off the, oh no, we got to leave those on. And this isn't the only real, the only solution, but it is certainly a solution. And let's also, so why don't you take it and pause and try and draw a picture on your own and see if yours matches mine. And so pause. And okay, we go. And so since f of 0 and f of 2 are both 0, we can put points at 0 and we can put it at 2. Now, I know that I have to have from negative infinity to 1, it has to be increasing and it has to go through 0. Now, I don't know how high it goes, so I'm just going to go up here to 2, and I'm going to say that I have a graph that has to look like this. Then at 1, I have to have a horizontal tangent line, and then it has to be decreasing after that. And so they don't tell me that it has to be 2. So if you had yours all the way up to 3, or all the way up to 4, or just at 1, that would also be acceptable. And this function is always concave down. So that's why my second derivative is less than 0. Well, that's all I got today, folks. Again, if you see any errors or you think I made a mistake, please leave a comment in the space below, or give me a question, or send me an email. And that brings us to the Star Wars fun fact of the day. In Star Wars Episode 1, Anakin Skywalker obviously created C-3PO. In Episode 2, he got a silver shell, and in Episode 3, he got a golden shell. So obviously, Anakin Skywalker knew what the golden C-3PO looked like. But in Episode 5, Empire Strikes Back, after they landed on Bespin, the stormtroopers blew up C-3PO and they ended up giving him back. So how is it that Darth Vader, the guy who made C-3PO, did not recognize that C-3PO was in the band. I don't know. It's one of those continuity errors that will always mystify us. All right, folks, that's all I got. Hope you have a good day. 25 minutes, not too bad. Not the shortest, but what are you going to do? Have a good day.